As usual, everybody is muted for the presentation, and if you want to ask questions, you can type them in, or you can click the hand raise button, and we can unmute you. If you have too much audio disruption, we might have to mute you again if that happens. We are recording this, and it will be put up on the website afterwards if you miss anything or you need to watch it again later. And we did apply for ResNet credits that haven't heard yet, but it's likely it will be approved to get ResNet credits as well. And I can send an email after the fact with all the details. So I'm going to turn it over now to Enoch Lenge, who's going to introduce our speakers.
Okay, thanks, Lori. As Lori said, my name is Enoch Lenge. I am the chair of the Professional Development Committee for the Northeast HERS Alliance. So I help put together these trainings, and I'm really excited about this training today because I am actively involved in a lot of projects that are using heat pump technology, whether it's single-family, multifamily, commercial use. I'm starting to see a lot more interest and applications for this type of technology, and I'm really excited to have our two presenters today because they cover a good perspective of the industry for heat pump technology and good experience with the technology. So we have Rick North with Mitsubishi, and he's going to talk about the technology, the heat pump technology, and what the different terms mean, and how it's available, what products are up and coming, and he's going to talk about that. And then first we're going to hear from Joe Swift, who is the operations supervisor here at Connecticut Light and Power, which is where I work as well. And he has some really good experience and some good data that he's going to share with us about the actual performance of these units in a couple applications and tested applications in Connecticut that we've seen here. So without further ado, I'm going to turn it over to Joe Swift.
Good. Thank you, Enoch. Just give you a little bit of background about where I come from with heat pumps. I've been at Connecticut Light and Power for a little over 15 years right now, and I kind of started getting involved in ductless heat pumps back in 2006, and I'm going to talk a little bit about the ductless heat pump pilot that we implemented in 2006 and where that took us to today in terms of our heat pump rebase. I'm also going to present some data on a heat pump that I owned in a previous house of mine, and in addition to those qualifications, just a little bit of background about other ductless heat pump experiences that I have. My mom happens to have 2 ductless heat pumps. One of my sisters has 2. My other sister has 1, and my brother has 1 ductless heat pump. So I've got a lot at stake here. I'll be the black sheep of the family if these units don't turn out to be reliable and efficient. So I'm a true believer, not just a utility guy here telling you about ductless heat pumps. Just some background. I realize the audience is, I'm assuming, primarily HERS raters, so you probably have heard some of this stuff before, but it bears repeating. Some of the inverter-driven ductless heat pumps have exceptional efficiencies. When I first came into the utility business many years ago, there was talk about cold climate heat pumps and heat pumps that had the capability of performing at temperatures close to 0, and it seems like those were more hype than fact, and it seems like when push came to shove and those units were actually tested under real-world conditions, they didn't quite pan out. That doesn't seem to be the case with the newer generation of ductless heat pumps. Some of them have efficiencies of COPs of over 4 or above at temperatures at a standard 47-degree rating temperature. My current ductless heat pump is rated at around a 3.5 COP at 47 degrees, as an example. Or, I'm sorry, 3.45 at 17 degrees. And obviously, they're ductless, so they don't have duct losses. Some of the newer models claim to have full or near full capacity at temperatures close to 0. Just a cautionary note, if you're looking to purchase a ductless heat pump, or if you're modeling a ductless heat pump for installation in a home, you really don't want to pay too much attention to the nominal ratings. So they're important, but really what you need to do is contact the manufacturer, somebody like Rick at Mitsubishi, who can get you kind of like a full spectrum of efficiencies and capacities, because what you're going to find is the nominal rating is somewhat arbitrary, and if you really want to drill down and do a good bin hour analysis, you really want to get maximum efficiencies, maximum COPs, as well as rated efficiencies and rated COPs, and use that to do any type of bin hour analysis. In terms of ductless heat pump use, I know Enoch tells me that we're seeing more and more of them in Connecticut, and I know we're seeing more of them in Massachusetts go into new homes, new low-load homes. It's an excellent application for low-load homes. Here in Connecticut, we're also seeing many units getting used to displace, not replace, but displace electric resistance heating systems. And we're also starting to see more and more of these units get installed to displace oil heat. Both of those applications offer significant savings opportunities on a retrofit basis. The first thing I'm going to talk about is a pilot that we ran here in Connecticut back in 2006, 2007. And essentially, well, the pilot actually spanned across into Massachusetts. Most of the results I'm going to speak to have to do with Connecticut. Essentially, there was roughly 130 ductless heat pumps that were installed in existing homes that had electric resistance heat. And the existing electric resistance heat was left in place with the idea or the objective that the ductless heat pump would be used as the primary heat source and the electric resistance would be used as the backup heating system. We had a third-party evaluator come in and analyze these systems, and the results are presented on that first table. You'll notice the sample size of 29 for the total heat. What that represents is 29 of the units that were installed, they monitored the ductless heat pump as well as the electric resistance heat, and they alternated between the two, and were able to get data for 29 of those units. And based on that, the savings came out to be roughly 2,300 or 2,500 annual kilowatt hours, depending on if you were in a Hartford or a Bridgeport location. Similar analysis was done on the whole premise, which compared the usage of the whole entire building, not just the usage of the heat, on a before and after basis, and came up with very similar results. And they did a billing analysis on just about the entire population. It was 124 homes that were put into the billing analysis, and based on that, the savings came out to be 2,700, 2,600 kilowatt hours, again, depending on the location. So, roughly we're talking, approximately 2,500 annual kilowatt hours for these units that were installed. Insofar as the cooling, some savings on the cooling. The savings was limited by the fact that some of these customers didn't have any cooling systems, so the installation of the ductless heat pump represented an increase in consumption versus savings consumption. But likewise, some of these customers had multiple window air conditioners, and in a situation like that, there was some savings. So it was a mixed bag on the cooling side, but there was a net overall savings for these homes. I didn't include it in this presentation, but I can tell you that when customers were interviewed, they ranted and raved about the cooling performance. And if any of you have actually seen a ductless heat pump on a day like today operate, you'd be I guarantee you're going to be satisfied with how quickly and efficiently and comfortably it cools the home, and then does an excellent job dehumidifying, because if it's because of the inverter technology, it can operate at a very, very low speed and provide superb dehumidification and very good comfort at the same time. One of the interesting things about the pilot that I'm showing you on this slide is the distribution of savings. And I'm going to talk about some of the factors that I think influence the distribution of savings. And I mentioned that the average savings was around 2,500 kilowatt hours for the customers that participated in the pilot. And what you see on this slide is the range of savings that some of these customers had. You notice that there was maybe a dozen or so customers that actually had negative savings or zero savings. So these customers represented people that ended up using more energy because of the ductless heat pump, or after the ductless heat pump was installed. Then you'll notice, as you move to the right on the chart, there were a few customers that saved close to 10,000 kilowatt hours of savings. And the evaluation, unfortunately, didn't drill down and get into the reasons why this distribution of savings was so varied. Obviously, some of it, when you do any type of billing analysis, it's going to reflect changes in lifestyle that can affect savings. Kids moving home from college, that type of thing. You may have some snapback buried into these numbers, meaning that customers may operate their system at a higher temperature set point because they know it's more efficient. But also, I think one of the drivers behind this data is probably customers not necessarily optimizing the control of the ductless heat pump, and I'm going to talk about that in some detail as we go through more of these slides. The next thing I'm going to talk about, this was this was the first ductless heat pump that I owned, and it was located in that room above the garage that you see on the bottom right. That room was about 550 square feet. It was, just essentially a bonus room. It was used as kind of like an office space above a garage. When it was built, the contractor said, well, geez, we can expand your existing propane system into that area, but it's going to cost a lot of money. And, the other option was to install electric baseboard or put in, so I opted for the electric baseboard. I said I'm not even going to consider expanding the existing propane system at a cost of, $10,000. So I had the builder put in some baseboard, and once he was done, I moved in and had the ductless heat pump installed. Once I had it installed, it was really a very good test environment for me. So I bought some data logging equipment and just kind of for the fun of it started logging data from the ductless heat pump, and lo and behold, 2 years later I had a ton of data, and I said, hey, this is good stuff. So I kind of wrote it up into a paper that we had published last year, and I was able to do some interesting testing throughout this time period that I'm going to share some of those results with you on the next few slides. Just a little bit of background about the building. It wasn't certified as Energy Star or anything like that, but it was well built. There was, the walls were 2x4s, but those were spray foam insulation, Icynene insulation. There was about an R50 in the attic and about an R30 spray foam in the floor. So it was certainly not what I would characterize as a low-load home, but it was built fairly efficiently, and it was a fairly tight structure. You'll notice on the diagram at the bottom right, essentially I had the ductless heat pump installed in the main living area. You can see the DHP designation on the floor diagram on the bottom. And primarily what I did is I alternated between the ductless heat pump and the Zone A baseboard, which is 14 feet of baseboard in that same zone. And essentially, for the most part, it didn't operate Zone B or didn't operate Zone C, the two baseboards in those zones at all. The assumption being that the ductless heat pump in Zone A and the baseboard in Zone A were going to be roughly comparable in terms of providing or supplying an even temperature to Zone A, and as well as helping to heat the subsequent rooms in Zone B and Zone C. So that was a key assumption, essentially assuming that these two units, even though they were located on different walls, they were still basically supplying the same room in roughly the same fashion and roughly at about the same effectiveness. Not cost effectiveness, but temperature effectiveness. And just a little bit of, just a picture of the data equipment that I used. I used data loggers to monitor the power for the baseboards as well as the ductless heat pump, and then I also measured both the indoor and outdoor temperature throughout the test. And so did this for essentially 2 winters, so I had a lot of good data to analyze when I was all said and done. What you see, the next chart that you see is what I'm calling the effective seasonal COP, and what the effective seasonal COP reflects is basically what I'm calling the technical savings. So the technical savings would be the essentially the actual COP of the unit, but plus some additional savings that was due to the fact that, you know, on cold days this unit didn't keep up. I knew it wouldn't. I expected that it wouldn't keep up, but if you were willing to, you know, put on a sweater when the temperature got below 15 degrees, you know, there was still some additional savings that you could achieve. So, you know, this chart basically represents the technical savings due to the equipment plus what I'm characterizing as the sweater savings. You know, the fact that I was willing to live with putting on a sweater when the outdoor temperature got very cold. And you'll see that the effective seasonal COP in this case is about a 3.5. It's just that it's the ratio of the height of those, the average ratio of the height of those 2 lines that I plotted based on the data that I collected. Now, if I look at what the actual COP of the unit was, you know, I basically plotted that by looking at the indoor temperature, or the amount of power that the unit used compared to the delta T, meaning the indoor temperature compared to the outdoor temperature, and I plotted those 2 lines, and basically the ratio of those 2 lines is the average is about a 2.9, and you'll notice that under very cold temperatures, you know, those 2 lines are a little bit closer together, so the COP under very cold conditions obviously would be a little bit less than 2.9, and under warmer conditions the COP would be a little above 2.9, but overall, you know, across the 2 years, I'm estimating that the unit itself performed at about an average COP of 2.9. I didn't mention this earlier, but it was not a Mitsubishi unit, Rick. Sorry about that. My new unit is, but so. but this unit didn't have the cold weather capability that some of the newer units do. But I guess 2 things. Number one, in Connecticut, I'm not sure if that's absolutely critical. It's nice to be able to say that your heat pump can operate at 13 below 0, but temperatures in Connecticut don't really reach 13 below 0 too often, or if they do, it's only for a couple hours a year. And the other thing that was interesting is this unit was rated down to about 7 degrees, but there were a couple of nights when it got down to, like, you know, 1 degree, 2 degrees, and I kind of took a chance and kept the unit running, and it still seemed to be doing something. So even though the manufacturer said, you know, rated down to 7 degrees, I was able to kind of push the envelope and even get it to do, you know, produce heat at, it appeared to be a COP at above 1, even on temperatures colder than that. This is a real interesting finding, that it wasn't, you know, when I noticed over time that when I walked into the room, you know, when I had the ductless heat pump on, you could almost predict how comfortable you were going to be, because it would always feel, you know, you'd always feel the temperature inside the room felt constant. It felt comfortable. And I noticed at the same time when I was running the electric resistance, some days I would walk into the room and it would feel really, really chilly, and other times I would walk into the room and, you know, it would feel almost sweltering. You know, my eyes would water and the air would feel really dry, and it would just feel, you know, and I looked at the data, and lo and behold, this is what I saw. The green line represents the temperature. This is just a typical day. I kind of picked this at random, but the green dots represent the temperature over time for the ductless heat pump on a typical day. And you notice like a little bit of a bump that took place. I don't know, like maybe 10 o'clock at night, but you know, I'm not sure, that could have been just the unit recovering from a defrost cycle, or maybe I opened the door and a little cold blast of air hit the thermostat and it overcompensated. But other than that, the unit typically did a very, very good job of maintaining very, very constant, even temperatures. counter that with the electric resistance. And when I plotted this, I was like, geez, no wonder I'm always either hot or cold in this room, because the temperature would go from 66 degrees, it drop down to like 58, 57 degrees, sometimes close to 56 degrees. The electric resistance would kick on, and the temperature would increase 7 or 8 degrees until, and then and constant not quite sinusoidal, but I mean constant cycling, which obviously really illustrated that the comfort effect that I was, or the lack of comfort that I was feeling with the electric resistance. The next graph, I took a stab at kind of estimating the capacity of the unit, and these were not direct measurements of capacity. I have to be honest about that. What I basically did is I estimated the heat loss of the building and plotted that on the blue line. And then I estimated, based on the temperature of the room under given conditions, what I thought the heat pump was putting out, and kind of plotted that. And as I mentioned before, the heat pump I knew was a little bit undersized, but that was perfectly okay with me, because I was still able to displace most of the load, and when I wasn't displacing the load, I was perfectly content to wear a sweater. But just to give you an idea that, at least based on what I saw and my best ability to put the data together and estimate the capacity, it seemed like the heat pump was operating within its rated specifications in terms of being able to produce heat even under cold temperatures. I mentioned before I ran producing heat at a COP that appeared to be better than 1. This is another interesting finding, this next slide, and this goes to what I said before about when you use a heat pump to displace heat, you really need to make sure that you control the heat pump effectively relative to controlling the existing heating system. And if that's not done properly, you can have very dramatic swings in your potential savings. And I think, again, going back to the pilot where I showed you that the distribution of savings, I think many of the customers that weren't saving because they were probably operating their heat pump and their electric resistance simultaneously, which can have the effect of essentially kind of beating your heat pump into submission and having it run on very, very low speeds and not having it do the work. I think the inverter technology is a great technology, but it also can be the Achilles heel of some of these units, because it responds it can respond in a negative way to outside sources of heat, which can cause the unit to essentially, reduce the output to the point where they can even stop running if there's too much interference from other sources of heat. So, with that said, essentially what I did is I looked at 4 different days. I ran this test for 4 days, and the blue line that you see on the left, the 4 different blue lines, were theoretical estimates of what the electric resistance would be if I just ran the electric resistance. Those weren't measured values, but I had enough data where I had run the electric resistance to basically say with pretty high confidence that on these 4 particular days, the electric resistance would have used about 20 kilowatt hours. Likewise, the green bars that you see, the bars that are all green, represent, again, not measured consumption, but the estimated consumption of what the ductless heat pump would use had I used it on those days. And again, I based that on the outdoor temperature and all the other data that I had collected. And you notice that the blue bars and the green bars show roughly that 3-to-1 ratio that would correspond to the COP of about 3 that I had mentioned before. So those seemed reasonable. And then what I did is I ran the heat pump, or during these 4 days, I ran the heat pump, and I also ran just the 2-foot strip of baseboard that was in the adjoining bathroom. I wanted to see what would happen when I tried to run the heat pump and the 2-foot strip of electric resistance that was in the bathroom. And essentially what happened is, the bathroom was nice and toasty, warmer than normal. but enough heat spilled out of the bathroom that it basically reduced the consumption, reduced the capacity of the heat pump. And really what happened in this situation is, if I compare just the blue bar and the green bar, my potential savings was roughly, maybe approaching 15 kilowatt hours a day. The difference between the, the 21, 22 kilowatt hours for the blue bar versus the 5 or 6 for the green bar. Just a 2-foot piece of baseboard in the bathroom produced enough interference and enough extra heat that spilled into the primary zone that my savings essentially got reduced to more than half. And I've seen similar types of phenomenon on my existing home, my new home with a ductless heat pump, that you need to be very, very careful when you're using ductless heat pumps to displace existing heating systems if you're going to keep those existing heating systems in place, because if the existing heating system is allowed to run to a temperature that's going to interfere with the ductless heat pump, it will. And the capacity of the ductless heat pump will drop, and the effectiveness of the ductless heat pump will drop, and your potential savings will drop. So that's kind of illustrated, hopefully clearly illustrated on this graph. And then lastly, I ran a test for about 3 weeks, and I ran this it was late winter, early spring, the first 3 weeks in March roughly. And what I did is I plotted the theoretical heat pump consumption based on the data, the rest of the data I had for the 2 years prior. But what I did during the test is when I left in the morning to go to work, I would just turn the heat pump off and just let the temperature drift down. And when I came home at night, whatever time, typically maybe 7 or 8 o'clock at night, I would turn the heat pump back on and get the temperature back up. And like I said, this was not a zero energy home or a low load home, but it was fairly well built, so the temperature during the day might have dropped 5 degrees, maybe 7 or 8 degrees, but it was manageable. And over the course of the 3 weeks, I was able to estimate about a 30% savings. And this surprised me, because a lot of the conventional wisdom about heat pumps, or what you hear people say about heat pumps, is that you should just keep them at a constant temperature and let them run and don't touch the thermostat. And that may be true to some degree. These results, I want to caution, these results, I did this test in early March, so it wasn't super, super cold. So I'm not sure if I could replicate these results in January, nor would I want to maybe replicate these results in January, because the temperature when I came home at night might be too cold. But at least based on what I did during the first 3 weeks in March, I was able to see some pretty impressive savings by employing setback strategies. So anyway, just to summarize, the ductless heat pump, based on the testing that we've done here with the utility, and both my testing at home, it was able to, they were able to maintain efficient operation. For the purpose of the pilot, we saw about 2,500 kilowatt hour savings. We're still trying to learn about how to maximize the savings, but I think I mentioned during the presentation, I think a lot of the savings potential has to do with knowing how to operate the ductless heat pump in conjunction with the existing heating system. If they're operated effectively, again, we saw COPs on my house of roughly 3, which would be comparable to the COP on some of the ground source heat pumps that I've seen tested over time. So, very, very impressive savings. And just to give you a little bit just a sneak preview of what I'm currently doing, you'll see the ranch house on the bottom right. I've got the Mitsubishi, Rick, so you'll be happy about that, but I've got a Mitsubishi unit installed in this home, and this home was heated by oil, and back in February, the oil company called me up and said, we were out at your house and we went to fill up your tank, and you didn't take any oil. What's going on? And I said nothing. I've got a heat pump that I'm using, and they said, well, certainly that can't do the job during the winter. But the bottom line is, I burned about 5 gallons of oil in that house this year, and used about a little over 3,000 kilowatt hours. So the heat pump was very, very effective at displacing oil. Again, I've counted some sweater savings in that, as I mentioned before. But certainly the heat pump, even if I discount the sweater savings, seem to be extremely effective at displacing oil. And I think it could be a good technology for the state of Connecticut and other states in Illinois to use as they kind of go after some of the potential oil savings that's out there. And I think that's all I have. I guess what we'll do is, if people have some questions now, I can address questions now. If not, then we'll kick it off to Rick, and we'll have time for, I guess, more questions at the end.
There was one question that's already been asked. It says, were there any other ECMs in the heat pump pilot?
I'm assuming ECMs with energy conservation measures.
ECM motors probably, Joe.
Motors? Yeah, well, I'm not sure. I don't know if it would matter, because what they did for the ductless heat pump pilot is they ran a test similar to what I ran. They basically had the customer run the heat pump for 2 or 3 weeks, and then they had the customer turn off the heat pump and run the electric resistance. So even if there were other energy efficient measures, they would have been captured in both the before and after, and it would have had a zero effect on what the net savings was.
Okay, there's a couple more coming in.
Sure.
Oh, yeah, Chad, who asked that last question, said it was measures. That's what it was, just to clarify.
Okay.
Okay, the next question, what about for heat pumps added for a house addition where the original house has a heat pump? Is there any potential conflict there?
I think ductless heat pumps are an ideal application for many additions. And again, the one thing I would be wary of is, depending on the configuration of the addition, you really want to maximize the ductless heat pump run times and maximize the ductless heat pump capacity. So if you're, there's no magic rule of thumb, but if you had the ductless heat pump temperature set point at 65 degrees and the older existing heat pump at 65 degrees, and a lot of that heat was spilling into the new addition, there's a very good chance that you're going to minimize the performance of minimize the capacity of the ductless heat pump. And really, the only way to do that is by trial and error. It's obviously there's many variables that would go into trying to model that type of scenario. So what I've done over time is, on my existing home, I've learned that I need to keep my oil thermostat 6 or 7 degrees lower than my ductless heat pump. If I try to keep it 5 or 4 degrees lower than my ductless heat pump, I'm usually okay. But I woke up at 2 in the morning, one very cold winter night, and I heard this rumbling, and it's like, what is that noise? And it was my furnace running. So that I kind of learned that when I said I burned 5 gallons of oil, it was by accident.
Okay, next one. Have you done any work or research looking at integrated controls for either electric resistance or fossil displacement?
No, but I think there's obviously, I think, a very big potential to develop or design integrated controls to ensure that you're maximizing the savings. And I think without integrated controls, you're relying upon the user to control, the ductless heat pump and the existing system effectively. And I don't have any hard data to support that, but based on the results of the pilot and that distribution of savings, my gut feeling is that some customers just aren't doing this effectively. And we received anecdotal information back from the pilot that elderly customers weren't used to using the remote control, and they were pressing the cooling button during the heating season. So I mean, it's there's evidence to support that there is, I think, a need for better better controls.
Okay, and then someone wants to know what your oil use was the year before, since you say currently you used 5 gallons. What about the previous year?
That's a good question. I just bought the house. The previous owner used anywhere between 600 and 700 gallons of oil per year. I was able to get their billing information. I did add some ceiling insulation, so I'm guessing that maybe I would have used 500. You know, but and I've done a lot. I've done modeling in REM rate, which kind of supports the 500 gallons of oil. Now, granted, I was a little bit frugal, and my bedrooms were a little bit cooler because it was a single zone system. So I probably would have to. A one-to-one comparison might be I traded 3,000 kilowatt hours at a cost of roughly $450 for 450 gallons of oil at a cost of like 1,200 or 13. So conservatively, I saved about $1,000 per year by using the ductless heat pump versus the oil, not including this plus what I would characterize as the sweater savings.
Okay, and Brian, this might have been answered, but he just asked, was the indoor temperature always 68?
No. On the results that I presented, I generally kept the indoor temperature at around 64 degrees. The smaller office and the bathroom, those temperatures typically would be a few degrees colder on cold days. On my current house, I generally keep the temperature like 61, 62, 63 degrees in the living areas, and the bedrooms, depending on the outdoor temperature, can be 55 degrees, and even a little bit colder on very cold days.
Okay, another written question. Would you recommend basic building shell improvements in poorly insulated air-sealed homes before investing in a ductless heat pump?
That's kind of what I have now. I guess you'd have to run the numbers. I put in Bluesome cellulose insulation as my attic because that was a no-brainer. But and I'm going to pursue other, I'm going to pursue some other option, some additional insulation in the walls soon. But I didn't go too crazy before I went with the ductless heat pump option. It makes sense. It obviously makes sense. I guess it's just really what you want to do. And being a heat pump junkie more than an insulation junkie, I went for the heat pump first because I wanted to use some of my equipment and run another field test.
This is Rick. I think what you'll find, though, is if you do the improvements on the building, you may be able to put in a smaller heat pump. I think that's where the benefit would come.
Right. You'll definitely be more comfortable. I mean, especially some of those outer zones will feel more comfortable. That's why I think you can really get away with ductless heat pumps on these low-load homes because they're so well insulated that you can just put in one unit on the floor and be able to maintain a pretty constant temperature throughout.
Okay, and then Dave asks, where was the power head located in the house?
In this, in the ranch, in the experiment that I had in the presentation, it was in that main area, and likewise on the ranch home that I showed at the very end, it's in the living room. So it's a typical ranch that living room that spills into the kitchen, and then the hallway. So it does a pretty effective job at heating 2/3 of the house, and the 2 bedrooms get a little bit chilly. Air conditioning is phenomenal. I love the air conditioning.
Okay, and the same, Dave had his hand up too, so maybe I'll just, in case he has more of that question, I'll see if I can unmute him.
Okay. Great.
So Dave, David Hiscox, you're unmuted if you have more of a question.
I'm all set, thanks.
Okay. And let's see, one more came in. What do you think of installing in a passive house?
I think it would be an ideal application in a passive house.
And then
we've seen, we have a few in here in Connecticut, and I'm sure there's others in Massachusetts and other areas as well.
And that person added on the ground floor in a passive house?
So you said they be on the ground floor, or?
Well, let's see. He's putting in a few things. It says, what do you think of installing in a passive house on the ground floor or on a two-story house? I guess there's sort of two questions in there.
Joe, you want me to take this one?
Yeah, I mean, I'm thinking
so this is Rick Norris with Mitsubishi. We've had some situations where people will use our product on a passive house, two-story, net zero. The issue usually doesn't have to do with performance, because our system, the loads on these kind of houses is so low that 9 or 10,000 BTUs might be enough for the whole house. We had one customer in the Worcester market who ended up putting 2 of our 9,000 BTU units in, one for the first floor, one for the second floor, and they only ran one at a time, though. They ran the first floor unit in the winter and the second floor unit in the summer, just to handle hot air rising.
Okay, great. Here's a few more coming in. Did you run a separate dehumidifier?
No, absolutely not. No, I mean, the inverter technology just will enable the unit just to run on very, very low speed, so it does a superb job dehumidifying.
I have a good description in my presentation about how the inverter works and how well it will dehumidify.
All right, here's another. How would you compare the ductless heat pump to replacing radiant ceiling heat in a 1970s or 80s multifamily project?
I think it would be a great application.
All right, and one more. Low-rise multis have low loads, so the heat pumps seem like a good fit. Please address distributions. Cold bedrooms would not be helpful for rental units.
You could do 2 heads, and again, you're right. I mean, cold. I mean, you can go as many heads as you want. Typically, I think to maximize the savings, you go with the first head. And if you're like me and you're okay with wearing a sweater in the winter, then you can get even more savings by just using the single head. Or doing more weatherization. Again, that'll help maintain even temperatures.
All right, I noticed Robert, who just asked that, had his hand raised, so maybe I'll see if there's more to his question.
Okay.
Robert, I just unmuted you. You still there?
I must have raised my hand by accident.
Okay. All right, then there's one more, and it is, what were your installed costs for each of the 2 homes?
The first unit was around, I think it was before any utility rebates or tax credits, was I think around roughly around $3,000. So it was obviously much cheaper than the $10,000 propane option that the builder had quoted me. And after tax credits and rebates, the cost was under $2,000. And my second unit was the Mitsubishi. So 1.5 ton, but 1.5 tons is kind of, again, that's the nominal size, so you really can't pay too much attention to that. But that unit was significantly more. I think it was a little over $4,000 before any utility rebates.
Okay, and there's 2 more. We'll finish those, and then we can switch over to Rick, who I just made you presenter. So you should be ready to go for that. All right, so let's see. Does that include the cost of the unit? Sorry.
That was everything. That was soup to
Okay.
nuts.
And then how is the fresh air introduced into the house?
These are not ventilation systems, so they have no bearing on the fresh air, although they do filter the air, so they will help with the indoor air quality. But on my existing home at the 1950s ranch, there really is no mechanical ventilation system as of yet. So.
All right, great. So that's the question so far. Now we can switch over and see what Rick has to show us.
Can you see my screen?
I do, yep.
Okay. Then I'll go ahead and get started. My name is Rick Norris. I work with Mitsubishi Electric. I've been with Mitsubishi for about 3 years, and prior to that, I used to sell ductless heat pumps as well as boilers and air conditioners for a contractor just outside of Boston, Massachusetts. So what I'm going to do is really, I don't want this to be a sales presentation for Mitsubishi. It's more when I'm out visiting contractors and homeowners, it's more about selling an idea of how ductless heat pumps will save people money. A lot of the different manufacturers have similar products. Obviously, we have some different things, but the other manufacturers have things also. What I like to do is show people that this is a rapidly growing business. If you look at this slide, the growth rate of ductless, now this is all ductless, this isn't Mitsubishi Electric, just in since 2005, is just rapidly growing faster than anything else in the HVAC industry. And one of the things I like to point out is we continued to grow even during the recession. So whereas everything else in our industry was dropping rapidly. The other thing I like to do is try to, dumbing down is the wrong word, I try to explain it in terms that people that are not in the HVAC industry will understand. And this is a great comparison. The fuel economy of a car is something that everybody understands, everybody gets. And everyone also understands that if you drive around a city, you're going to burn a lot more fuel than when you drive on the highway. There's many reasons for that. Most people realize, hey, you're stopping and you're going around the city, and there's stoplights and you're accelerating, but on the highway you can put it in cruise control. That's what the inverter is like. It's sort of like cruise control for air conditioners. To give you a better idea, this is a description of how a normal single-stage ducted air conditioner works. It goes from 0 to 100% instantly, and because, unfortunately, most homeowners will turn off their air conditioners on a hot day, they really shouldn't, but they do. It could take 12 hours to cool a home once you get home. It takes a long time because a properly sized air conditioner, is properly sized for the design day, which in the Connecticut, Boston area is in 85 to 90 degree range. I'm not sure what everyone is on this call, but you're going to be in that range. So a properly designed air conditioning system is sized properly for 1 to 2 days a year on average. So because by definition, a design day is that 99% of the time you're below that design temperature. So it's oversized the majority of the time, which means it's going to cycle. So this is where the cycle process starts. And when a air conditioning system is off, the temperature rises. Obviously, that's the most obvious, but so does the humidity level. And humidity is what causes discomfort in New England and the Northeast. So conversely, here's how an inverter works. So an inverter, we apply just enough energy to get the compressor spinning. So once the compressor is spinning, it's very quiet because all we're doing is applying a very small amount of energy to get it going, and then we can accelerate it. Once we are accelerated to, say around 130 hertz is the frequency of the power, we're able to give you more BTUs for that single room than the central air would have been. Now, a lot of people say, yeah, but then you're oversized. So what we do is we lower the temperature for that room very quickly, but we're not dehumidifying during that time. And then once the room gets to temperature, now it drops way down to, say 30 hertz, which is also about 30% output. Now, this is where we dehumidify. It takes a lot less energy to maintain temperature in a space than it does to lower temperature in a space. So by getting the temperature down quickly and then ramping down to about 30% output, we're burning a lot less energy, and now we're dehumidifying. One of the things that any inverter system does that might surprise people is that the indoor fan will stay on if the system is on. Part of that is to move air around a space and to keep even temperatures. But the other part is that it's actually measuring temperature at the indoor unit. And in order to measure that temperature, air has to be passing over the coil. So this is how it does it. And by measuring that temperature, it is able to keep the set temperature so even. One of the things that Joe had on his slides was how even the temperature was. And that's because of the inverter. It's able to adjust almost like a cruise control on a car that I had mentioned earlier. It's able to adjust the power output to maintain the temperature. Now, one of the things that many people don't realize, and until you point it out, that everything in your home is zoned. From your lights to your faucets to your stove to your refrigerator to your televisions if you have more than one. Most people have everything in their house zoned except for their air conditioning system. Most air conditioning systems are still single zone, and so people have come accustomed to dealing with a single zone air conditioner, even though they're not comfortable everywhere in their house. So this is give you a good idea of what it would look like. So here's your lights, here's your faucets. Here's your typical house, right? We have lights in every room. Everybody's used to that. It's always been normal operating procedure that you can turn on and off lights as you go into a room. But everyone's used to one thermostat, which is nothing more than a switch, except the switch that's controlled by temperature. And throughout the space, up in the Northeast, we have many homes that have furnaces in the basement. If you have a furnace in the basement with air conditioning, your second floor might be 10 degrees, maybe 15 degrees warmer than the first floor, because the thermostat's on the first floor and there's no return going to the second floor. So that's really what people have come used to, whereas a great application in a scenario like that, we put a ductless heat pump upstairs, take care of that 15-degree difference. So I'll go into quickly to the types of different products. Joe was talking about he had 2 different brands in his 2 homes, but you had, I believe, wall-hung units in your house, Joe, and there's other options. The wall-hung unit is what people are used to. So these are just happen to be some of the samples that that Mitsubishi has, right? So single-zone systems, that's the most common. That's the workhorse. That's what the niche is that the product was originally brought to the United States to fill, and that would be hot and cold spots, an addition, a finished attic, a finished basement. I remember when I was doing in-home sales, I sold it for a mother-in-law suite, where the mother-in-law had moved home and she wanted her room a completely different temperature than anyone else in the house. So they put one of the systems in, and her room became its own zone, and she could keep it whatever she wanted. So this is our hyperheating system, which is other manufacturers are coming up with something similar. This is the low temperature heat pump. Most people still don't believe that heat pumps work in New England. I know Joe did all that study and that they'll work to super low temperatures, but if I ask somebody is minus 13 degrees cold, most people will agree that that's very cold. And these heat pumps will work just fine. This one, this particular model will work down to minus 13 degrees. Not all of them will. Most of them are rated down to 5 degrees, which is still pretty cold, and it's still well below the design temperature in most of the Northeast. If you get up into the northern parts of Maine and New Hampshire and New York and Vermont, it gets a lot colder than that. So this is just a couple things about our product. I won't really go through that. There's more salesy stuff. This gives you an idea of what the actual output is at these low temperatures. So one model, you're going to get 21,600 BTUs at 5 degrees, and you're still going to get about 15,000 BTUs at minus 13. So that's, for those people that understand baseboard, that's about 30 feet of baseboard, which is plenty of heat. There's many rooms that you can't even fit 30 feet of baseboard in. So this is another type of system that's available. This is a ceiling cassette. Not really applicable to most homes. It's a lot of people use this in drop ceilings and More and more people are using these on second floors maybe. You end up having to cut some joists and head them off for this to fit because you do need access to the different size. But a lot of times you won't have enough space between the floors to use it on the first floor. So just quickly go through this. This is a ducted unit. This is becoming very popular in the Northeast especially, where there are some people that will not, they are offended by trying to put something on their wall. So this is something, a solution that you could provide where you have a ducted solution. Now, where people get into trouble with our ducted systems is that you try to put too much ductwork on these. You still, one of the guiding principles of ductless systems is zones and small zones. You don't want to try to do an entire second floor with one of these systems because they only get 0.2 inches of static, which means you can't really put much more than, say, 10, 15 feet of trunkwork on it. If you try to exceed that, you better have a really well-designed ductwork system. Otherwise, you're not going to get the airflow out of it that you want. All these systems are quiet. All the wall-hung units, the ceiling cassettes, the ducted systems. 23 decibels is this system. Some of those wall-hung systems that I showed were as quiet as 19 decibels. And so, I mean, these are super quiet systems, especially when you think that a library, which most people would consider as quiet, are around 30 decibels. Okay, so because this kind of system would be in the middle of an attic, you have a built-in condensate pump to handle any kind of condensate. Air filters. This is ductwork. I do get the question all the time: does a ducted system need a return filter? And yes, it does. Just like any other ducted system, you need a return filter. Okay, multi-zones. This is probably the fastest growing part of the business, and the reason I believe that is because more and more people are trying to use these as whole home, as a whole home solution for a typical house. The question was asked earlier for a two-story. So you can go with a multi-zone for a two-story. Now the nice thing is the systems can ramp down, super low outputs, and to match the loads. All of the multi-zones, I believe all of the manufacturers, they're all inverters, and I believe all of them are heat pump only now. It used to be that there was a couple manufacturers that still had some cooling only multi-zones, but I think that they've gone away and that they're all heat pumps, which in the Northeast, it doesn't make any sense not to go heat pump. Multi-zones you can really match any of our indoor units with, so you can mix and match, and you can do 2 to 8 indoor units. I believe all of the manufacturers now have an 8-zone available. In the northern climates, because especially right now it's 95 degrees, but this weekend it's supposed to be in the 40s at night. This is the time of the year where people can really start saving some money, especially if they use oil heat or propane heat. So this gives you an idea of what the breakdown is, and this is based on information from the last census. So it gives you an idea of what the breakdown is of sources of heating fuel for all the different states in the Northeast. So Joe's in Connecticut, so 34% of homes are using natural gas, and that number is only going up because the state's trying to increase that. But then all over New England and the Northeast, it's pretty high for natural gas. But fuel oil is also a pretty big source of fuel. in the Northeast. It's not a big source of fuel anywhere else in the country, but it is still huge in the Northeast. And propane, I believe, is in this number because it's a delivered fuel. And believe it or not, there's still a lot of electrically heated homes in the Northeast. And Connecticut offers huge rebates for electrically heated homes to put in these, and other states do also, because obviously electrically heated homes would be the highest, and I can show you those numbers in a couple minutes. This is a breakdown of what's the breakdown of where people are spending their money, and I show this to contractors when I visit them. That their biggest opportunity is the business that my HVAC contractors are in the heating and cooling. Obviously, there's what you guys do with with home performance isn't taken into account in this because you could make the pie smaller. Ultimately, the size of the pie is what you guys control. It doesn't really change the all the percentages. Although I guess if the envelope was improved, then that heating and cooling cost would go down, and the other numbers really wouldn't change that much. There's two big opportunities for ductless heat pumps. The retrofit opportunity is the majority of the market. This is where you go in and you're going to leave the existing heating system in place. So somebody asked earlier about replacing ceiling radiant, which is, I'm not sure, most likely those are electric panels. So if you're going to do something like that, you probably want to leave the panels in place and put the ductless heat pumps in, and then that way the radiant panels would only be necessary when the ductless heat pumps can't keep up, which isn't very much. Depending on where you are, you're talking 20% of the winter, 10% of the winter. Not a very large part of the winter. And then the other big opportunity is the net zero passive house. The biggest issue with these homes, that the HVAC industry is having a hard time understanding, and most HVAC contractors can't quite grip it, is that some of these homes could be as low as 10,000 BTUs for the whole house. And that, many manufacturers, and I'm not talking ductless, I'm talking boilers, I'm talking furnaces, they don't make anything that small. So a ductless heat pump is a perfect application for that. And then last thing I'm going to show you is this is just a spreadsheet that I have made just to give people an idea of exactly what kind of savings you'd be looking at and compared to other sources of fuel. So I'm just going to put in some numbers that are local to me. I live in the Boston area, so I'm going to use 18 cents per kilowatt hour. And up here, I think we're around $3.79 a gallon for oil. Propane, I just heard a number this morning down in Connecticut. It was $2.59 a gallon. And natural gas, the last number I heard was $1.40 per gallon. Now, if you notice, I'm putting in distribution losses of 10%. And I'm not going to use wood and wood pellets because this is in a spreadsheet, and Enoch has this. So if you wanted that, you can. The reason I'm not going to include it is these ones are not very accurate because this whole spreadsheet, this is nothing but a math problem. We know that gas gives you 100,000 BTUs per therm, and we know that propane gives you 90,000 BTUs per therm, and oil gives you 140,000 BTUs per therm. Wood, on the other hand, depends on a lot of things. How dry is the wood? What type of wood is it? So these two numbers are not really very accurate. So all this spreadsheet does is it converts everything into what would a million BTUs cost. So I'm assuming a 95% gas and propane system and an 85% oil system. And then this it converts everything to here's what a million BTUs cost for the different sources of fuel. So obviously, electric is the most expensive, at $52.74. But then you have oil and propane. And one of the things that surprises many people is they did not realize that propane and oil are a similar cost for a million BTUs. So you're not going to be saving sorry about that. Hopefully that doesn't happen again. You're not going to be saving a lot of money using that. Now, the COPs, Joe was talking earlier about what the actual COPs are. So he was finding, COPs in the 3 range the majority of the time. So, if you look at this, $17.58 for a million BTUs with a COP of 3. And a lot of our systems have COPs of 3 in the 25 to 30 degree range. And then the majority of the winter, though, we're actually over here. COP of 4 at $13.18. So that's some pretty significant savings for a good chunk of the winter. So I'm going to go ahead and close this and just get to the last part of the Okay, so we have, this just gives you some ideas of what the, what the heating hours are in the Northeast. So here's Boston. So 74% of the time you are above freezing, which is when our COPs are in the 3 to 4 range. Worcester, Massachusetts, 65% of the time we're above freezing. Hartford, Connecticut, 64%. Albany, New York, 60% you're above freezing. New York City, 80% of the time. So these markets are perfect for these products. So, Lori, I don't see any questions on mine. Maybe that's just because I'm in projection mode. So let me get out of this.
Okay. There are a couple of questions from Kevin. So you should be able to see if you go into the question section, if you scroll all the way.
Yep, I see it now. I see it now. When I was in the presentation mode, I couldn't see anything.
Okay, great.
So let me go up. So Kevin
Hanlon is the one that you would start.
Yep. Okay. Okay. So it talks about geothermal versus air source heat pump. I'll go ahead and read the whole question. So, one of the benefits of geothermal heat pump over the air source heat pump is the presence of a favorable heat sink or supply versus the lack of that sink or supply with air source. Can you discuss this? Geothermal, a lot of the systems have higher COPs because they're more consistent. They're dealing with, usually 6 feet under. The temperature is much more consistent. Where geothermal many times is going to lose the argument is the install cost is significantly higher in geothermal. Right now there's a huge tax credit for geothermal that goes away in 2016, I believe. And where the air source heat pumps don't get that kind of 30% tax credit, I think ours is $300. That will, right now, geothermal with that 30% tax credit is very appealing to a lot of people. I think for a whole home solution, I think that the geothermal is probably a good solution if it's a large home. But for the smaller 4-zone systems, it's probably the air source heat pump is probably the better solution. Let me go down and see if there's any other questions. No, I'm not. Okay. Okay. Contact information for me. I don't know if you want me to email that to you, Lori. I could get it over the phone. It doesn't matter to me.
Sure, that's fine.
My email address is rn as in Nancy ORTZ at hvac.mea.com. Okay. Now, maximum number of indoor units versus the outdoor unit with an HSPF of 10 or better. Okay, you're probably 10 or better. I don't know. I don't have that information handy right now, Andy. On the multi-zones, I know we have a couple of systems that do reach Energy Star, but I'm not sure if the HSPF is above 10. Let me see. What did you mean on the slide that said heat pump only, no cooling? Probably that might have been the multi-zone. The multi-zone systems are only available in heat pump. They're not available in the cooling only. Okay. So did I miss any questions?
You might have answered already. Did you see the one from Kevin? The first one. How many?
About Geo?
1-ton unit.
Oh, hold on. Maybe I didn't go to the first Kevin question. All right. can you state how many BTUs a 1-ton unit can produce at 0? Well, that depends on which 1-ton unit. So our 12,000 BTU unit, is rated, at around 12,500 BTUs at 5 degrees, and it's going to give you about 70% of that at -13. So it's almost a straight line. So you're probably looking at, in the 10 to 11,000 BTU range at 0 degrees. So our ratings are at 5 degrees, and then we have at -13, not at 0 degrees exactly. Let's see, and what would be the COP? The COP of our systems that low, it's not. I don't know exactly what the COP is. I believe it's around 1.5, but I don't know exactly. It's not in the data. It's the lowest COP we actually have is down to 17. I assume a high-end Mutsu or like product. Usually in most systems, obviously as the temperature goes down for all the manufacturers, the COP goes down. Once you're getting down to the 0 range, you're at the highest COP. Most of the time, as long as the systems are working and keeping up with the heat load and the heat demand on the space, it's going to be more efficient than oil and propane. And obviously electric. If it's working at all, it's more efficient than electric. Okay, then that's where I started, was the geo.
I think there might be a few more at the bottom.
At the bottom? Okay.
And then, did you answer that one? Does inverter tech in cooling and heating mode explain?
Let's see. Inverter tech in cooling and heating. Inverter tech, I guess I don't understand the question.
Okay.
Does he want to explain the question maybe?
And you can either write something new or raise your hand and I can unmute you.
Does heat pump exclude cooling? No, all heat pumps are also air conditioners. You can have cooling systems that are not heat pumps, but any heat pump is by definition also an air conditioner. To clarify the term heat pump, I'm not sure. I mean, I'll give you the layman's term. A normal air conditioner, if you were to, when it's on in the summertime, and you'll go outside and you'll put your hand on top of the air conditioner and it's blowing out hot air. So what the air conditioner is doing at that point is it's taking the hot air using the refrigeration cycle and from the inside and extracting it and discharging the hot air outside. All a heat pump does is that there's a part in there called a reversing valve. So you're going to reverse that process. So you're going to pull heat from the outside and discharge it inside. That's all you're doing it. And believe it or not, all you need is that the temperature of the refrigerant just needs to be colder than the outdoor air to absorb heat. And then that's where the refrigeration cycle comes in to discharge that heat into the inside of the house. Okay, let me see. Inverter technology. Okay, inverter. I mean, like I said, I'm not sure exactly what they're looking for in the inverter. In the basics, the inverter technology is all that's saying is that the ability to control the power of the system, of the compressor. And so a normal air conditioning system is restricted at 60 hertz. The inverter allows you to control that power to vary between, say, 30 hertz and 130 hertz. Well, when you change the power input, you're changing the speed of the compressor. So you're speeding up and you're slowing down the compressor depending on what kind of power you're applying to it. And if you're spinning really fast, you're getting more BTUs out of it in both cooling and heating. And if you're spinning slower, you're getting less BTUs out of it in both cooling and heating. And it's obviously quieter because you're blowing less air. Okay, next question. With regard to retro installations, what is the best sales approach to sell multi-zone splits with one condenser and dealing with the line sets all over the building? Let's see. Is it more advantageous to sell multi-single zones? I've seen it done both ways. The issue you get when you're trying to do, let's say you have a 4-zone house, so you have one approach is put 4 condensers outside and 4 indoor units. And obviously you have less line sets going around the outside of the house, but you have 4 condensers. So there's a disadvantage there, because a lot of times most people don't have room for 4 condensers. I saw one house had 6 condensers once, and it looks a little strange when you have that many condensers around. Whereas if you wanted to do one 4-zone system, the approach that most people take is go through the basement. If it's an unfinished basement, you can tap into the basement, run across the basement, and then come out the other side and up that side of the house, so that you're not really wrapping around the house. The other option is go up into the attic and go across the attic to get to the other side of the house. As long as you don't exceed your 82 feet, then you're good. If you're going to be more than 4 zones, now your options are you either go with a single 8-zone system, or you could go with 2 4-zone systems. So you could do, put a condenser on each side of the house, and that way you have less line sets going around. So I'm not sure if that answered your question, but most of the time use your basements and your attics to get to the other side of the house. Is inverter technology available in both cooling and heating modes? The inverter is always, it doesn't matter what the mode is, it's always going to be inverter technology. I mean, we do have a non-inverter technology that's a cooling-only mode, but we don't sell that much of that in the Northeast. Explain the advantages one more time. So the advantages, really the advantages of inverter technology is I'm going to go back to the car example again, cruise control. The system will, let's say it's set at 70 degrees, and it's going to run the system at a certain temperature. Well, let's say the temperature outside rises, and then all of a sudden it can't, it's finding that the indoor temperature is rising, and now it's up to 71. Well, now it's going to know it needs to apply more BTUs, so it's going to speed up the compressor to match the load, just like a car would if you're going up a hill. So the biggest advantage of the inverter is it's going to apply just enough power to match the load, no more, no less. So that's really where the advantage is.
Yeah, I think, Rick, in terms of sizing, that's a big advantage too, because you really don't have to, size these units to the 3rd decimal place, because you could just approximate the size, and the unit's going to really match the load continuously as well. So if you're not sure whether to put a 9,000 BTU unit in or a 12,000 BTU unit in, it doesn't matter. Just put a unit in.
That is true for the most part. The only place you have to be careful on that, like for our brand, for example, between the 15 and the 18, actually I think it's the 18 and the 24. Your low on the 18 is 3,800. But the low on the 24 is 8,700.
Right.
So that's the only time it makes a difference, is if you're trying to choose between one of the systems where the low mark is significantly different. Because then, if 8,700 is oversized, then maybe you should have gone with the 18, because that one could have ramped down much lower. But for the most part, you're right. It is not. Sizing is much easier with our systems. Is there a difference in terms of efficiency between heat pump and AC cooling mode? Not really. If anything, the difference in efficiency isn't what you think it is. The difference has more to do with in cooling mode, you're trying to lower the temperature by 15 to 20 degrees. And so the issue is that you're only trying to lower 50 to 20 degrees. But in heating mode, now you're trying to raise the temperature, in some cases, 20, 30, 40, 50 degrees. So people might view that the heat pump is less efficient, but it's actually working a lot harder than it was in air conditioning mode. So hopefully that makes sense. Okay, is the inverter technology an example of a variable speed system? Sort of. It is variable speed, and it matches the load. Most people think of variable speed, GE has their ECM motors, and that's what people view of as variable speed. So these are, variable load. They're going to match the load. So it is sort of variable speed, yes. In older retrofit homes, what about winter comfort condensation in closed bedrooms at night with the primary heating system not zoned in bedrooms. Now, condensation. In the winter, why I don't understand why there would be condensation. Our systems in heat pump mode don't give off any condensation. They only give off condensation in cooling mode because it's pulling hot air, hot moist air over a cold coil, and then the water drips off outside. But when it's in heat pump mode, it does not give off any condensation. Do you know what they might be talking about on that, Joe?
No, I don't. No, I mean.
Okay. So if you wanted to raise your hand and ask that question again, I might be able to understand it. Condensation from occupants on cold walls and windows. It shouldn't be caused by our system. Like I said, our system is just providing a heat source. Unless you're talking from the distribution standpoint, that but a lot of times, believe it or not, a higher percentage of homeowners than not, if somebody's not in a room and they have a forced hot air system, they actually close the vents, which isn't good. It actually puts stress on the rest of the system. But a lot of people are already doing that. Okay, did I answer all of them, Lori? It looks like I might have.
Yep, I think that's all of them. Anyone else have a question? Otherwise, I think we can thank Rick and Joe for an excellent presentation and thank everyone for coming. And I did learn during this call that we did get approved for ResNet credits, so I will send out an email explaining how to go about getting those for anyone who's interested. And I think that can wrap this up. Thanks a lot, everyone. And
okay, thank you, everybody.
We'll see you next month.
Great, thanks.